Hi, I'm Bob Alexander. I have here a Wang 300 series calculator. It works great, but there are three unusual things about this calculator. The first is it's not connected to an electronic package. It's only connected to a 12-volt power supply. These Wang consoles are actually just dumb terminals. They've got the keyboard and the display and nothing else in them. They had to be connected to an external electronic package box that did the actual calculations. But this one's different. The other unusual thing about it is that when you turn it off, it's a nixie clock. It shows the time, month, and date. And the third unusual thing about it is that you can configure it as a reverse Polish notation calculator, just like a Hewlett-Packard calculator, except it has nixies. So I bought this console on eBay. When I got it, the cable to the electronic package had already been cut off and discarded. The electronic packages show up on eBay from time to time, but they're expensive. People are asking $1,500 to $2,000 or more. They're also often broken. They use discrete diode transistor logic, 3 different voltage levels, and core memory, so they're a challenge to repair. So I designed a modern circuit board that fits inside the console and brings it to life without altering any of the original vintage hardware. Once I had this, I was able to implement a clock and a reverse Polish notation calculator using JMOS. But first, I needed to understand how to drive the display. The display board, like the electronic package, requires 3 different voltages to drive the multiplexing logic, and I was having a terrible time trying to get the nixies to light up. While Googling for information, I came across a website by Brian White, which I'll link to below. He has a great story about how he obtained his Wang calculator, but when he got it, it wasn't working. He had to repair it, and he did an excellent write-up of his work on his site. As luck would have it, Brian lives just a couple towns away from me. He was kind enough to have me over. He was able to verify that my hardware was working. He was able to help me understand how to drive the hardware. And even since then, I've referred to his site dozens of times for all the great information he's documented there about the Wang calculator. So, Brian, thank you for making your website. Thank you for helping me out. I could not have done this without you. So here's the board. It's based on a PIC32 microcontroller, which is more power than this application needs, but I like programming in C++. Power comes in, ground in 12 volts. It gets scaled up to 24 volts. The logic on the display board, the nixie board, requires -11, 0, and +11 volts. And I map the 0 volts, 12 volts, and 24 volts to that. And the display board is fine with the slight over voltage. I scale the 12 volts down to 3.3 volts with this cute little switching regulator here, and that supplies the microcontroller. I have a board that I got off eBay for high voltage, and that scales it up to the 250 volts for the nixie tubes. I have a couple of level shifters on the back to shift the 3.3 volt logic from the microcontroller to the higher voltage for the nixie display logic. I have a GPS for getting the time, and the antenna will be facing the sky once it's installed in the console. The clock comes on when you turn the power switch on the console off. So I can't let the power be shut off to this board when the clock is operating. So I have this jumper. If you put it here, there will be no clock when you turn the console off. But if you put the jumper here, it will bypass the console's power switch and supply power to the board even when the console is off, and we'll be able to operate the clock. I'll show you later how the board fits in the case. First, let's go through the features. When you plug it in, we get the time. We turn the unit on and we're in the calculator mode. We can do things like 3 plus, 4 plus equals 7. But look what happens when we do a multiply. If we do 3, enter, 4 times equals, we get 12, but did you see the flickering? The original Wang calculators did that too, and I've reproduced their behavior. The Wang does not do multiplication and division directly. Instead, it takes the natural logarithms of the operands, adds or subtracts them, and then takes the antilog. This was one of the big innovations of the Wang calculators, and it's described in their patents. Anyway, the logarithm calculations are being done in the display register, and that's why you see the flickering. You're seeing the calculation in action. I have to give a shout out to my brother Steve at this point. The Wang calculator patent describes how it calculates logarithms, but I couldn't figure it out. Steve is really good at math, and he helped me grok how the Wang calculator uses just addition, subtraction, and decimal point shifts, all operations that are easy for 1960s hardware to do, to calculate logarithms. So, Steve, thank you for helping me on this. But if the Wang is using logarithms to calculate multiplications and divisions, how does it handle 0? There is no logarithm of 0. Mark Palmer helped me figure this out. I found him on YouTube, where he has videos showing various vintage electronics and other projects. I've included a link below. He has a working Wang calculator, and he's all set up to make and post videos. I sent him about a zillion tests to run, probing the boundary cases in the Wang's behavior. He helped me discover and understand some really interesting quirks, which I've replicated in my code. So my third shout out is to Mark Palmer. Thank you for all your help. So let me show you what I learned. Let's start with the log of 0, which mathematically is undefined. But the Wang calculator thinks the log of 0 is minus 41.269 blah blah blah. And I've reproduced that behavior. I'm not sure why the Wang has this particular value for the log of 0. It's not naturally produced by the algorithm it uses for taking a log. Maybe it's hard-coded. The patent doesn't talk about it. For my implementation, I hard-coded it. The antilog of minus 41 is about 1.5 times 10 to the minus 18, which is a really small number. Wang is basically using that as an approximation of 0. The largest number you can enter into the Wang is 9 nines, and if you multiply that by 1.5 times 10 to the minus 18, it's still a really small number. So any numbers you're likely to be using with the Wang and multiplying by 0 will still look on the display like they're 0. But if the Wang is only using an approximation for 0, what happens when you divide by 0? Let's try it. Clear all, 1, enter, 0, divide equals, and you get a really big number. Well, it's dividing by the antilog of minus 41, meaning it's dividing by a very small number, and so the result is a pretty big number. And you'll notice that the overflow light is flashing. That means that the actual result is this number you see times 10 to the 10. Again, this is the original Wang calculator's behavior. I'm just emulating it, so don't blame me. Okay, so we've played with the calculator for a bit. Now it's time to get serious and test the keyboard. These units are 50 years old, and very often the key switches have corroded and need to be replaced. So I've implemented 5 applications on this calculator. There's the Wang calculator application, there's the reverse Polish notation calculator application, there's the nixie clock, there's a configuration application, and there's a keyboard test application. You enter the clock application by turning the console off. You go back into the calculator application by turning it back on. The other apps are entered by holding down the key for 4 seconds. To get into the configuration app, you hold down the enter key. To get back into the calculator app, you hold down the clear all key. To get into the keyboard app, the problem is whatever key I chose for getting into the app, that might be the key that's broken. So I made it so that holding down any key except the aforementioned Enter and Clear All keys brings you into the keyboard app. Here, every time you press a key, the key code appears on the display. You can test the toggle switches too. Switch 1 is now in the off position, switch 1 is in the on position, switch 2 is off, switch 3 is off. If you press a key and it doesn't change the code, that means that the key is broken. Fortunately, compatible switches are still available. You can buy them at places like DigiKey, but they're a lot cheaper on eBay. Once you've tested the keyboard, you can go back to the calculator app by holding down the Clear All button. Finally, let's look at the reverse Polish notation calculator. We go into configuration mode and go to option 9. When it's 0, the calculator emulates the Wang 300 series. When you change it to a 1, it becomes an RPN calculator. By the way, don't let the Wang's Enter key fool you into thinking that it's an RPN calculator. It's not. The Enter just takes a logarithm and adds it to the logarithm register. To do addition and subtraction, you use the entirely different plus and minus keys. Yeah, it's sort of using postfix notation for addition, subtraction, multiplication, and division, but so do adding machines and cash registers. It's not behaving the way an HP RPN calculator does. The RPN calculator that I implemented for this does use a 4-level stack. It behaves as you would expect an HP calculator to behave. Once we're emulating an RPN calculator, we don't need some of the keys that the Wang calculator uses. Specifically, we don't need separate left and right adder keys. We don't need the clear adder and recall adder button. So I use those keys for other functions, and I made up some replacement labels for them. The new functions include 1 over x and y to the x, base 10 exponent and logarithms, trigonometry functions and their inverses, swap x and y, roll the stack, and a function shift key. So now we have an RPN calculator with a 4-level stack, just like the classic calculators from brand X. We can do 2 enter, 3 times, 4 enter, 5 times, plus, and get 26. Calculations are done with 64-bit floating point numbers, so there are about 15 decimal digits of precision. You can't enter exponents, but if you produce a large number, it will display a mantissa, a space, and the exponent. If you produce a small number, like minus 41 e to the x, you again get a mantissa, an exponent, and the decimal point in front of the exponent indicates that it's negative. You can change the display precision by hitting the shift key, which causes all the decimal points to light up, and then a digit. So if I want 2-digit precision, like for financial calculations, I press shift 2. You still have full precision with calculations, but it rounds the display to 2 digits after the decimal. The product accumulator switch has a new purpose in life. It now switches between degrees and radians for trig functions. So if we set it to degrees and take the cosine of 180, we get minus 1. If we switch it back to radians and take the inverse cosine, we get pi. The multiplier accumulator switch has also been repurposed for the RPN calculator. It turns engineering notation on or off. So we can type 1, 2, 3, 4, 5, 6, press enter, and switch to engineering notation. And numbers are shown with a power of 10 that's a multiple of 3. So it's easy to see kilo, mega, giga, milli, micro, nano, and so on. Let's talk about configuring the clock. As I said, the clock gets time from GPS satellites, but that only gives it the universal or Greenwich Mean Time. To configure your time zone and the daylight savings time rules, you go into the configuration app. There are 9 different settings you can configure. This number here indicates which setting you're at. This shows the value of the setting. You can move through the different values for the setting with the plus and minus key, and move on to the next setting with the enter key. So this setting, setting number 1, is for 12 or 24-hour display. Then you have a choice of the display format, hours, month and date, or just hours and minutes. This is the time zone. All 38 time zones of the world are entered into here, and you can move through them. I'm on the east coast of the United States, so that's universal time minus 5 hours, so I'll set it to that. Then there's the daylight saving time configuration. You can set it to 0, which means there is no daylight saving time. Set it to 1, which means daylight saving time is on. And set it to 2, which means it automatically switches between daylight saving time and standard time based on the rules you enter in the next 4 options. This is the month that daylight savings time starts. I'm in the United States, so daylight savings time starts in the 3rd month, March. 2nd week of the month, and you can move through here. 1, 2, 3, 4, 5 means the last week of the month. And it assumes Sundays, and that's true in most places of the world. Then daylight savings time ends in the 11th month, 1st week. Now we go back to the calculator app by hitting clear all. Turn the console off, and we're back to the time. A neat feature is that every day at midnight, the clock will spend 1 minute cycling through all the digits in the display. This is to prevent cathode poisoning, which is a problem nixies can have, where if a digit is unused, material starts to accumulate on it and blackens out the digit. You need to exercise the digit periodically to burn the material off, and we do that here. Okay, to install the board, we have the console, we have the board, we have the power jack, and a little wire to go to the board. Turn this over. There's 4 screws you need to remove. So there's 2 edge cards. One is wired to the cable coming in from the electronic package, and we remove that. And it's being held in with a screw. We replace the screw because it's also holding in the display board. So my cable was cut off by a previous owner. It's probably useless, but I'll save it just in case. There's another edge card, and that goes to the display board. We disconnect that. And then this board has 2 edge connectors here that I soldered in at a right angle. And we want to line these up, and it's a little hard to do because you can't see what you're doing if you do it like that. So I'm going to tilt it, and now I can see into the edge. Alright. The display card gets plugged into this connector, and if you look closely, there are the letters A through S here. And there's also the letters A and S on the board, so you know which way to plug this in. We have a power jack. We screwed that in to the hole where the cable used to be. And plug the power into the board. It's keyed, so we can't plug it in the wrong way. We want the clock feature, so if we didn't want the clock feature, we'd put this jumper here. If we do want the clock feature, we put the jumper here. It's labeled clock enable, off and on, and that bypasses the power switch on the console, so that even when the power switch is off, this board and the nixies will still have power, and we'll be able to detect the power switch is off because it's actually a dual pole switch. So there's another signal that the microcontroller reads to know that the power switch has been turned off and goes into clock mode. So there you have it. It's a nifty Nixie clock, and when it's time to balance my checkbook, I can switch it into a great RPN calculator, and for historical accuracy I can always set it into Wang calculator mode. I hope you found this interesting. Thanks for watching. Bye.